So in the last hour, we did a lot of theory, organizing data, talking about vocabulary and stuff like that. Now we're going to actually get into some numbers and start doing some calculations. So let's say we have a set of numbers. Now I'm going to use a relatively small set of numbers just to make it easy on myself. And I'm going to put them in order to make it even easier on myself. Like this. Now, again, what I'm doing here isn't real practical. That's a small enough set of numbers with only 5 numbers. I can look at it pretty quickly and get an idea of how it sets, especially with it already organized from smallest to largest. But I'm just doing this as an example. The first thing I'm going to define about that is something called n. N is the size of the group. In this case, n equals 5 because there are 5 items in the group. Okay, now from there, we need to talk about how would we describe a set of numbers with just other numbers rather than having that picture of a graph or whatever. To do that, I'm going to go back to drawing pictures, talk about something called a distribution. A distribution is basically a number line that's got things plotted out. It's a number line that goes from the smallest value up to the largest value, and it has plotted out how many items take on each value. A simple distribution would be a dot plot. Let's say we have numbers ranging from 8 up to 17. And let's say we've only got one item that has the value of 8. We have 2 items that have a value of 9, 2 that have a value of 10, 4 that have a value of 11, 6 that have a value of 12, 5 that have a value of 13, 3 that are 14, 2 that are 15, 1 that's 16, and 1 that's 17. There's a distribution. It shows how many of the values lie at each point along the possible values. Well, this is discrete data where we have only certain values. What if it was continuous data where we could have values in between the numbers? Well, what that distribution would then look like is just this. We have the numbers down here, and I'm not going to bother wasting the time to fill them in. We'd have some sort of curve like this that shows, the higher the curve is, the taller the curve is here, the more items in the sample have that value. So this is the tallest part of the curve. That's the most common or most popular value in the sample, or in that group of numbers. Well, in nature, data tends to fall on a normal curve. The normal curve looks like this. It's what so many of you, when you were younger, probably heard referred to as the bell curve. And that bell curve, remember there's a number line down here. That bell curve can be described with really only 2 different features. One, where's the location of the center? In other words, what number on the number line is below the center of that curve? And 2, how wide is it, or what is its spread, or dispersion it's sometimes called. This black curve and this green curve are roughly the same spread, they're the same width, but the center of the green curve is up here, it's higher than the center of the black curve. Whereas this blue curve has the same center as the black curve, it's just wider and much more spread out, has more spread. So for tonight, we're going to start talking about measures of center. And you've probably heard of pretty much all of these before. Pretty common if you do any sort of basic statistics in your younger classes. Measures of center include the one that we're probably most familiar with is the mean. The mean is what most of us have always referred to as the average. To do the mean, you add them all up and you divide by how many are there. So we're going to do 12 plus 18 plus 19 plus 22 plus 29. We already said n equals 5, so we know there's 5 of them there. So we had that. We got 30, 49, 71, 100 divided by 5 is 20. So that one has a mean of 20. Next, the second measure of center is a median. The median is the middle number. So to do the median, we have to do 2 steps. One, we have to put the numbers in order. We already have our list of numbers in order, so that step is done. 2, we need to find the location of the median in this case. Now, in a set this small, we could actually go and cross off the first and the last. The first and the last, what's left in the middle is the median. But if it's a larger set of data, like 200 numbers or 300 numbers, we need to be able to find the location. And the way we do that is we take n times 0.5. So for this set of data, n is 5. So that'll be 5 times 0.5 is 2.5. Since this is a decimal, we would round up. So 2.5 would round up to 3. What that would mean is the third number in the list is the median. 19 is the third number in the list. That's our median. So 19 is the median. Let's say that wasn't, if n equaled something other than 5, that wasn't a decimal. So I'm going to give you another list here. Let's say we have 3, 9. Again, I'm going to put them in order. So here's a list. What's n equal in this list? 1, 2, 3, 4, 5, 6. So n equals 6. So how do we find the location of the median? 6 times 0.5 is 3. If this is an integer or a whole number, no fraction or decimal. What that means is it is between that number, the third, and the next one, in this case the fourth. So 10 is the third, 12 is the fourth. The median is between 10 and 12. So we add those two together and divide by 2. The median of that group would be 11. The 0.5 is because it's halfway. The median is halfway, in the middle. So 0.5 is 50% times 0.5, yep.
What did you get to get that?
Well, up here I got 2.5, which meant you round up. Since you get a decimal, you round up. It's the third spot, the third number in the list. Here we got 3. Since it wasn't a decimal, since it was a whole number, that means it's between that spot and the next spot. So it's between the third and the fourth.
If it's ever odd.
Well, that's, yeah, when n is odd, that means it's going to be, there's going to be a middle number. So you just round that decimal up and gives you the location. So if n is odd, you're going to get a decimal here when you multiply by 0.5. So you round up. That's your location. If n is even, you're going to get a whole number here. It's going to be between that one and the next one in the list. Why did I divide by 2? Because I'm trying to find between 10 and 12. Now we know we can look at that and say 11 is between 10 and 12. But if you don't, you can add them together and divide by, average those two numbers together, basically is what I'm doing there. The third measure of center is called the mode. The mode is the number that appears most often. Now in the list I gave you, no number appears more than once, so there is no mode in that list. There's another measure of center called the mid-range. The mid-range, you take the smallest number and the largest number. So the largest number would be called the max. The smallest number is called the min. You subtract those and you divide by 2. So up here we had the smallest number of 12, largest number of 29. I should not subtract them, you add them, sorry. So we have 12 plus 29 divided by 2, that is 41, divided by 2 is 20.5. Which you can see, that comes out relatively close. We had a mean of 20 and a median of 19. So that's, mid-range is pretty close. But the mid-range, again, is a pretty quick and dirty way of getting a center. The two, almost everybody will agree, the two best measures of center are the mean and the median. Which always brings us to the argument, which one is the best, the mean or the median? Well, let me show you an example. This is one of my favorite examples of accurate statistics that are just flat out lies. Perfectly accurate statistically, but just not honest.
Bias, not honest? Or?
Well, stick with me. 1983. University of Houston. You don't need to write this down. Sorry, not University of Houston. University of it's blanked out there for a second. I'm just going to throw it in. I believe it is Arizona at Santa Fe. I remember right. Advertised that the average starting salary of a 4-year marketing graduate, so someone graduating with a bachelor's degree in marketing, was just right around $78,000 per year. Now, for those of you that don't remember 1983, in 1983, the average starting salary for a high school teacher was between $16,000 and $17,000 a year. $78,000 a year is phenomenal money. I would probably walk out of here right now for $78,000 a year. That was accurate. It was the truth. That was the average starting salary. What they neglected to tell you was that one of the graduates was a man by the name of Ralph Sampson. Ralph Sampson was 7'4" and was the 2-time NCAA basketball player of the year. Drafted number 1, signed like an $8 million contract with the Houston Rockets. It takes a lot of $20,000 marketing graduates to average out an $8 million contract to $78,000 a year. Mr. Sampson was the only one in that group that made more than $33,000 that year. But that's the accurate mean. So I bring that example up because everybody thinks the mean is so wonderful. You put numbers in a formula, you crank them out, it's great. But the median is more stable. It's what we call more stable. The median of that number was in the low to mid $20,000 range for those salaries. But let me show you how this works. Let's say I have a set of numbers. Now I'm just going to throw a set out here. Let's find the mean of this set of numbers. You guys go ahead and find the mean for me. So is it 17, 28, 31, 41, 58 divided by 5 is what? 11.6 works for me. Well, the median, that's pretty easy to find. It's the middle number is going to be 11. Pretty close. The mean and median are both pretty close. Well, now I'm going to do this. I'm going to add a number to it. I'm going to add the number 40 to it. Now the mean would be what? 15.83. The median is going to be between 11 and 13. It's going to be 12. So you can see adding that large number, the 40, changed the median a little bit. Went from 11 to 12. Is it 16? I thought it was 16. Okay. But it changed the mean from 11 to 16. A huge jump in the mean. So the median is more stable if you have really large, or what we call extreme values, really large or really small values. So those are our measures of center. Now, sometimes we're not given this huge list of numbers. Sometimes the numbers are already organized for us. We might be given a frequency table. Let's say we're looking at number of cars in a household and their frequency. Let's say that none of the households we surveyed had more than 5 cars. So let's say we've got 0 is, let's say we had 4 households that had no car, 48 households that had 1 car, 37 that had 2 cars, 5 that had 3 cars, 4 that had 4, and 2 that had 5. So there's our numbers. Let's say I want to find the median. Well, to do any of these, I have to find the total here. What's the total of this? I got 4 plus 8 is 52, 89, 94, 98, 100. Good, that's what I was shooting for. So n equals 100. That's what that means. There's 100 items in this, 100 households that were surveyed here. The median, to find the location, we take n times 0.5. So that will be 100 times 0.5, which is 50. Now, since that's an integer, it's a whole number, that means it's between the 50th and 51st number, right? So now we just need to figure out where the 50th number is. Now remember, we're putting these numbers in order from smallest to largest. So the smallest would be 0, right? That's 4. If we went up to 1, how many would there be that have 0 or 1? 52 total. That's bigger than our 51, isn't it? That means the 50th and 51st number are in that group right there. So the median is 1. The median is 1 car per household. Well, how about finding the mean? To do the mean, it's a little more work. To do the mean, we're going to do the number times the frequency. Why are we going to do that? Well, because there are 4 families that have 0 cars. How many total cars is that? 0. There are 48 families that have 1 car. How many total cars is that? 48. 37 families have 2 cars, so 37 times 2 is 74 cars. 5 families have 3, there's 15. 4 families have 4, that's 16 more, and 2 families have 5 cars. That's 10 cars. So we add this up, and what do we get? I'll let you guys do it. Okay, I lied. 163? Yeah? Okay. 163 total cars. So the mean is that total divided by the total frequency of 100. Oops. 163 divided by 100 is 1.63 cars. That is our mean. Simple enough? Good. Well, the next thing we need to discuss are measures of spread. Again, how wide that curve is, how spread out the numbers are in our set of numbers. So if I give you a set of numbers, like that. One measure of spread is simply called the range. The range is simply the largest number, which we call the max, minus the smallest number, which we call the min. The largest number here, since I put them in order, is 18, minus the smallest is 8. This has a range of 10. Now, unfortunately, I can come up with another set of numbers that also has a range of 10. Would you say that they're equally spread out? I would say that this set over here is a lot more spread out than this set. So the range is not a real precise measure. It doesn't distinguish between sets of data real well. So we do something a little bit more telling, and that is the standard deviation. Tied in with the standard deviation is also something called the variance, which is just one step short of the standard deviation. So I'll point that out when we get to it. So let's take those two sets of numbers and let's go through and find the standard deviation of it. Standard deviation is a 6-step process. I am not even going to write down the formula for the standard deviation because it's ugly and scary and, oh, I don't want to do that to you. We'll just go through the steps. Step 1 of finding the standard deviation is to find the mean. Casey's sitting there thinking, I had him in class 4 years ago. He's gone soft, right? Maybe. Don't want to make the math teacher mad and make him get tough. There's 5 numbers there, so we're going to add them up and divide by 5, and we get a mean of 13. Step 2. Is to subtract the mean from each number. So I have my numbers 8, 11, 13, 15, and 18. I'm going to subtract my mean of 13 from each. So 8 minus 13 is a negative 5. 11 minus 13 is a negative 2. 13 minus 13 is 0. 15 minus 13, 2. 18 minus 13 is 5. So all I did is I just subtracted the mean from each of the values in the original set of numbers. Step 3 is to square that value. Now we have to be careful. If you don't punch this in your calculator correctly, if you type in negative 5 squared, it might try to tell you that it's negative 25. We know that's not true. When you square a number, it will be positive. Negative 5 times negative 5 is positive 25. When you put it in your calculator, you got to put it in parentheses like that. Negative 2 squared is a positive 4. 0 squared is 0. 2 squared is 4. 5 squared is 25. Step 4. Find the total of those numbers. So this is what, 29, 58. Here's your total. That's step 4. Step 5 is a little tricky. Yeah, total of these numbers, yep. Step 5, I'm going to give myself some room. We're going to divide by n minus 1. So for these numbers, n equaled 5, because there's 5 numbers in the list. So that means we're going to divide by 4. 5 minus 1 is 4. Which means we're going to get 14.5. That number right there would be the variance. If we were asked to find the variance, we would stop right there, and that would be it. But to find the standard deviation, there is a 6th step. Step 6 is square root. Because there's 5 numbers in the list, but we're dividing by n minus 1. So if n is 5, we're going to divide by 4. So we do the square root of 14.5. Gives us 3.74. Oops, the decimal point goes there. You know, every now and then I look around the room and I realize I could say whatever I wanted to, and you guys would write it down and repeat it on a test. I taught this last semester. I taught a bunch of classes for the architectural design program because I had an instructor walk out at the last minute this summer. And during their structural engineering class, that thought crossed my mind several times. Not only does nobody in this room, but nobody else in this building has any clue what I'm teaching right now. Yeah, the little evil voice sometimes talks. We suppress him now. So anyway, that's the standard deviation to 3.74. Let's take a look at that other set of numbers and see if we get a different standard deviation now. 8, 9, 13, 17, 18. You guys tell me what to do. What's step one? Find the mean. I'll race you to it. It's 13. I'll let you double check it. When you're finding the mean, by the way, and you're adding them up, make sure before you divide by 5 or divide by n, you hit equals first and then divided by 5. Otherwise, it causes some really interesting answers. You guys get 13? Okay, what's step 2? Here, subtract that 13, the mean from each. So we have 8, 9, 13, 17, and 18. And we are going to subtract 13. So what do we get? -5, -4, 0, 5. Cool. Step 3. Square each. Okay, so what's -5 squared? 25. -4 squared? 16. 0 squared? 4 squared? 16 and 20. Step 4. Is the total, so we get 82. It's not my fault you're slow. No, I'm just kidding. Sorry. Step 5. Divide by n minus 1. N is 5, so we divide by 4. That number right there would be called what? The variance. Ever use it? If I want the standard deviation, what do I still have to use? The square root of the 25, or 20.5, which will give us 4.53. Notice that is larger than what we had up here. We had 3.74, so that tells us that data set is more spread out. What do you think? Could be worse? Okay. I think what I'm going to do is I'm going to cut it off right there. That's enough for the first week, especially with the weather being bad out there.